Hello, so this video is going to be on 2 versus 3 electrode cells and why you absolutely should care when assembling your system. So a cell configuration for a 3 electrode cell can look something like these two images here. Over this side, we have a very simplistic cup cell. All we have is a reference electrode, a counter electrode, and a working electrode submerged in an electrolyte. Same thing over here, but we have a swage lock cell configuration. We have the working on this side, the counter on this side with our active material here and the electrode counter material here. And then we just have a reference electrode in the top. For a 2 electrode cell, it is literally the same thing, just no reference electrode. So this is the exact same for a cup cell, no reference. Same for the swage lock cell, but no reference. A coin cell is also referred to as a 2 electrode cell. So I'm fairly sure you're thinking, why should we care? As most people use either a 2 or a 3 cell system all the time without really giving it much thought. It's just out of habit. So to show you why we should care, I'm going to use a simplistic 3 electrode system. We're going to use a swage lock configuration. So exact same thing, we have the working here, counter here, and a reference electrode here. But for this system that I use, it's going to be non-aqueous, and we have 2 glassy carbon electrodes down the bottom here. We have a silver iron reference electrode. Our electrolyte is tetraethyl ammonium tetrafluoroborate in acetonitrile, and our potential window here is going to be 0 to 2 volts. And for this example, I'm using cyclic voltammetry at 100 millivolts per second. When we have our cell hooked up to the potentiostat, when we either read or apply a potential, it is going to be the potential difference between 2 electrodes in the cell. For a 2 electrode cell, it is going to be reading the potential difference between the working and the counter electrode and would normally be hooked up like this. We also have a potential difference for a 3 electrode cell, between the working and the reference electrode, so the potential difference across here. We also have another potential difference across the counter and the reference electrode here. So this is not super important. I just wanted to include this in case you wanted to try this yourself. But to do this experiment to show you why it matters, we needed to synchronize 2 channels. So we have our counter on this side, our working glassy carbon on this side, and our reference up here. So we have channel 1 and channel 2. So channel 2 has the counter and reference wires hooked up to this glassy carbon and the working wire attached to the working glassy carbon. For channel 1, we have our working wire here connected to the working electrode, and we have the reference channel up here connected to the reference electrode. We don't need to worry about this one because obviously if we want to find out the potential difference across these two, we just subtract the potential difference across these two. So this is some of the results that we got for this system. We just have a very standard cyclic voltammetry curve at 100 millivolts per second, nothing too different. This cyclic voltammetry is showing the potential difference for the 2 electrode cell setup, so the green wire here, and we are measuring the potential difference and the current across the working and counter electrode. So this is where things get really interesting and shows you why your electrode configuration really matters. So this graph here, on the y-axis, we have our cell potential for the potential difference across our working and counter electrode. So just here to here, basically simulating a 2 electrode cell configuration. Remember, our potential window is 0 to 2 volts. So as you expect for our CV, we go from 0 to 2, back down to 0. A nice triangle, very simple, and what we expect, 0 to 2 volts. So remember, we had another channel hooked up doing the orange over here, so connected to the working and the reference electrode. So that is this graph here, and it is referring to this axis on this side for the potential. So we've gone from 0 to 1 and back down again. And you would expect, since we are applying a 2-volt potential across the working and the counter, that the working electrode would have 1 volt and the counter electrode would contribute 1 volt or negative 1 volt in this situation. So for our counter electrode, just across the potential difference across the reference and the counter is this blue potential down here. So it looks roughly like it's kind of gone to -1, but it hasn't really. So to really show this, I am going to just make the counter electrode response here an absolute value. So it's going to be positive, so they all overlap. Okay, so now the counter electrode response is an absolute value and everything here is a positive response. For our 2-electrode system, we expect, as we apply with the potentiostat, a 0 to 2 volt response. And we expect that we would have a positive 1 volt and a -1 volt response on our counter and working electrodes here. That is clearly not the case. So on this axis here, we have 0 to 1 volt. If that was the case, both the orange and blue line should be going exactly from 0 to 1 up there, back down to 0 again. But that is clearly not the case. The potential is not equally shared across both the working and counter electrodes. We have a much smaller response on the counter as opposed to a larger potential response on the working electrode. To also highlight this again, we have the 2 cyclic voltammetries basically showing what each electrode is doing. So the working electrode is on this side, which is much larger. As you can see, it's going from 0 to almost just a little bit above 1.1 volt. And then the counter electrode, which is going from 0 to just a little bit over minus 0.8 volts. So there is a very significant difference in a very simple setup. No porous material, no material on the counter either. That there is a very big difference between working and counter electrode potentials and what your potentiostat is actually measuring. So the verdict: does it actually matter your cell configuration? Yes, it absolutely does. If you are looking at your working electrode and you have a 2-cell configuration and you apply for this example, a 2-volt potential, then your working electrode for this system is not actually going to be the assumed 1 volt. It's going to be 1.1 volts. This absolutely matters when you're doing CV, galvanostatic charge discharge, float tests, anything. If you're trying to characterize your system and you're using the applied potential that you use for your calculations, whatever that may be, it is not going to be actually representative of the actual potential that is applied to the working electrode. So if you're if you want to look at your working electrode or counter electrode, whatever that may be, you absolutely need to be using a 3-electrode system, not a 2-electrode system. Otherwise, you're going to have inaccurate results. So it therefore becomes really important to ask yourself what you're actually trying to achieve with your system. If you are trying to take an analytical approach and find out an intrinsic property of your, say, electrolyte or electrode material, then you want to, yes, use a 3-electrode configuration. If you want to see how all of these things interact with each other and basically replicate a system in a commercial scenario, then yes, you would use a 2-electrode cell system. So just to reiterate here, for a 2-electrode cell, if you want to see how all of these things behave together, so your electrolyte, your binder, conducting agent, basically the whole system, how they interact with each other, then yes, 2-electrode system. But if you want to characterize just the electrolyte or just the binder, or just the electrode material, then yes, you want to use a 3-electrode configuration so you can accurately determine what your potential is on your working electrode and how that is going to affect either your electrolyte or electrode material. So if you're curious about what was discussed today, you can go check out this paper here, as it looks at the exact same electrode system, except in an aqueous system. And it also discusses the effects of your spacing between your counter and working electrode. This article here is still yet to be submitted, but I absolutely recommend giving it a read over. It just talks about the fundamentals of electrochemistry and how you actually should assemble your cell, and what you should think about when you're trying to characterize capacitive systems and pseudocapacitive systems. It's not too heavy. It's actually quite simplistic as far as papers go in electrochemistry. But yes, absolutely, please give this a look at if when it has been submitted. Thank you for watching. Bye.